And what we will plan to do is to release the assignment, but I'll give you 1 week after after the break, so that you have enough time to like enjoy the break and then come back and worry about the assignment. Okay, so let's present this. Okay, so what were we looking at? We were looking at contextual small step semantics, and the whole point of contextual small step semantics is to ensure that lot of these what we call as administrative reductions, right, which is basically some things like these, or you have a sequence of commands, you evaluate the subcommand, can be reduced into separated into what is known as the evaluation context. Just to repeat what I mentioned yesterday, evaluation context is a command with a single hole, right, and the hole could be filled by an arbitrary command. And the way to read what is here is that evaluation context always has a hole, right? You can fill the hole with the command, any command at all, and you just get the command as a result. The only other interesting evaluation context in our simple language is sequencing. So the way to read this is that you're sort of instructing how you should view the execution of a sequence, right? Which is that if you see a sequence command, you evaluate the first component of the sequence, right? You sort of narrow down on that. That could itself be a sequence. You keep doing this, right? Until you reach the command which does not fit this structure. And then what you do is you sort of apply one of the actual step rules to evaluate it. And how can you fill this evaluation context with the command? Again, recall that any evaluation context, right? This thing is an evaluation context. It has a single hole in it, and that hole could be filled by a command. And this is sort of a syntax for plugging a hole. So given this evaluation context and the command C, if you want to plug the single hole that is there, all you do is you recursively plug it here, right? So you sort of plug that in the right position, and you keep doing that until you actually get a command. So the thing to remember is that on the left-hand side, what we have is a pair of. You can sort of think about this as a function, right? It takes a pair of an evaluation context and the command. On the right-hand side, you have a command. So even though these things look like this, we will encode it as a relation, obviously, because we want to use relations to inductive relations to be able to prove things easily. So we won't do it as a function, but that's essentially what it is. So what is this bias, right? It sort of gives us a way to separate out interesting steps from the boring steps. Here there is only a because we actually said how to evaluate a sequence, right? If you can take a command, the evaluation context for a semicolon is that you sort of focus on the first one, right? So now we have two levels of small step semantics, essentially two relations. One is what we call a step 0, that's the lowest level, right? Another what we call a step C, that's the command for stepping through evaluation context, right? So essentially what it says is if you have a valuation and a command, and you can split that command into an evaluation context C and the actual command C, right? And if you can take a step from this B comma C using the step 0 relation, which is the interesting set of smaller steps, to V prime C prime, then all you do is this whole thing reduces to V prime, where C prime is plugged for this hole, right? So you sort of separate out the outer context, and then you can take a subcommand and take a single step. You just take the command, plug it back into the context. So this, in combination with how we describe the evaluation context, sort of stands in for this, right? If you have a command like this, then you can always split it into an evaluation context that looks like this, right? And you apply this rule, which says that you can take a single step of the smaller subcommand, right? This will be C1 in C1 semicolon C2. And if C1 can be reduced from to C1 prime, then you plug that back in. But otherwise, the rest of the commands remain the same. The only observation is that this C1 semicolon C2, right? The equivalent of this particular reduction is gone. That's no longer there. It's no longer there because evaluation context help us to describe how it steps through. So it may be instructive to actually step through how the evaluation proceeds, right? Um, it's instead of so one key property is that at every step now, right? We are going to describe small step semantics as a transfer flexive closure of this top level thing, right? So at every step, you will have to pick a subcommand to evaluate, right? And the subcommand itself might be the entire command where the evaluation context is just a whole. But that's the thing that you have to identify at every step. I mean, you can automate this, but that is the new thing that is going to appear. So instead of the reduction steps being instead of the reduction steps only containing these arrows, there are going to be these equal to, where we take a command, right, and then we split it into an evaluation context and a subcommand, right? This evaluation context and the command that fills the hole, so that we can actually call this step 0 function. So that's the idea here. So what are we doing here? We are evaluating factorial, right, which we've seen earlier with input 2, and this is showing a first couple of steps, right? A few steps, and then we sort of skip something, and then we finally go to the result. The way to read this is that this is the valuation, right? So the valuation, empty valuation, input is 2, and the command is this entire thing. So we need to reduce this, right? And if we want to apply this contextual small step semantics, we have to split this into first an evaluation context and a command that we are actually going to reduce. The thing here is that this is C1 semicolon C2, right? And the meaning of this is that when you see C1 semicolon C2, then your evaluation context is sort of zooming in on this one, right? So essentially what we end up doing is that our evaluation context is built into this. This is the evaluation context, right? The term here, it has a single hole, right? And factorial loop appears here. And the command that actually fills the hole, right, is this output -1. So observe that this is equal to, right? We are actually saying these two configurations, these two states are equivalent, right? So all we are doing is that we are sort of transforming this into transforming a single command into an evaluation context and the command that you actually want to reduce. This is what we will keep repeating every step. Okay, so that's the crux of what we are going to do here. And what's the point, right? We've split it. What is the point? Then you can actually reduce this command, right, that fills the hole with one of these. And we are going to apply this assignment rule here, right? And once you do the assignment rule, you plug it back in, right? So this does the assignment, right? So it extends output to 1, and then this evaluates to skip, right? This evaluates to skip, and the skip fills the hole here. So once you fill the hole, this becomes command again, right? So this whole thing is now a command. So now, if you want to reduce this, you have to sort of be clever here, right? So the thing is, this entire thing is the command, right? Skip semicolon factorial loop. If you happen to split it again into a whole and factorial loop, right? It will appear as if there is a whole factorial loop, and this command will be skipped. But observe that there is no transition. This step 0 transition that reduces a skip, right? So if you have a skip as a subcommand, there is no possibility of taking a step. But we do have a step for skip semicolon C2, right, which just goes to C2. So the way we actually split it is that we say this command skip semicolon factorial loop can be considered as, can be split into a whole for the evaluation context, right? There is no outer context, just a whole. And the whole command becomes just the command that fills in the hole. right? This whole thing becomes the command that we are going to reduce using step 0, and we are actually going to apply this rule. So this whole thing reduces to just C2. So this whole thing reduces to factorial loop. When you fill the hole with the command, you just get the command back. So that's why we have factorial here, right? You have to keep doing this again and again. Factorial loop is a while command. So while is a single command. So again, we split this into a whole and a factorial loop, right? And yeah, um, yeah, then you do the while loop application, right? So while true, so this splits into one iteration of the loop, right, followed by the while loop again. This is exactly what we have here, right? When you have a while and this termination is not true, you split it into the body of the while loop, semicolon, the while loop again. That's what we end up doing here, right? And the point here is that now you have C1, right? Consider this assignment to be C1, semicolon C2, and the whole thing, semicolon C3. Now, now the observation is that we know what the meaning of this is, right? Intuitively, we want to reduce this command now, right? And so we actually make the evaluation context to be this whole thing. Essentially, this command becomes the whole, right? The whole thing is evaluation context, and the command that we are reducing is this assignment. And you keep doing this over and over again. That's really the idea. So this is how the evaluation proceeds, and eventually you'll go to skip. This might seem like a tedious addition to what we had, because we only have this single administrative reduction in the original thing, right? But typically, if you extend the language to have more interesting structures where commands can appear everywhere, then this sort of splitting into evaluation context and the interesting rules sort of makes sense, because you will always have just this one top level thing, and then sorry, I take that back. You might have more than one top level thing, but all of the interesting rules, right, are going to be described in step 0 function. We will look at an example later in the class today. Okay, so let's actually dive into the Coq definition, right? So what are the components that we are going to have? We are going to define what an evaluation context is, right? An evaluation context is a whole, or it's a C-seek. We distinguish that from the seek command. It's actually a context sequencing, where this could be a context itself, right? So that describes what we see here, right? That's just an encoding of the data type. Okay, that's fine. The next thing we want to have is this, right? Capture this plugging. And as I mentioned before, we are going to capture this plugging as a relation, right? It relates a evaluation context, a command that fills the hole, with the command that you get when you fill this hole with this command, right? So this is a whole command, right? That is going to be captured as a relation. So this plug is that relation. So it takes a context command and then relates that with the command that you get as a result of filling this context with the whole. So we have one first rule which says that if you plug a hole with the command, you just get the command as a result. The second one says that it captures this behavior. So you have a semicolon here, right? Sequencing command, and the command that you plug in here, and you get the plugged version, which is essentially captured here, right? So you have a sequence, you have a context here, C2, right? I plug the hole that is here in C with C, the small c. And the way we describe that is because we are going to plug the hole in C, if you plug this capital C with a small c and you get a C prime, right? Then this whole command is going to be just sequence of C prime. C prime is just a command, right? C prime, C2. This is precisely capturing what we have here. Okay, so that's the plugging. So we've defined these two steps, and now we have to define these step 0 and step C. So step 0 is sort of the same thing. There is nothing different. I just use a different constructor name here. The only thing that it doesn't have is it doesn't have a step for sequence C1, C2. It only has sequence skip C2. And all it says is that if you have a skip, you can just go from this command to C2. Right? Otherwise, it's the same thing as what we have seen earlier. Okay. So this is the step 0 function. And we recover the meaning of the original program, right? The top level thing is given by this rule, right? It says that if you can reduce the subcommand, then you can reduce the entire command. That is sort of captured by a single thing, right? So you can C step from VC1 to V prime C2 if you can sort of split C1 into an evaluation context C, right, and the command C and the subcommand C, right? And the subcommand C can be stepped using the step 0 function, step 0 relation that we defined here into C prime V prime C prime. Then if you plug C prime back into C, you get a C2. Then this whole thing just becomes V prime C2. So we are just describing what we have here. We've written this one as C1, this one as C2. This one as C1 and C2. Just so that our proof rules, when we apply backwards, right, it sort of goes through. The point to remember here is we are always going to unify this with the goal term, right? If you directly write complex term here, which is say plug of C, capital C, small c, C1, then Hawk is going to sort of complain, I can't unify this. I exactly want whatever you have here to be a plug thing, right? So that's the reason why we sort of split it this way. But otherwise, the meaning is the same thing. Okay, so that's C step, right? And the thing to remember is that we are not describing a different semantics. We are just describing a different way of writing the same semantics. So we will, in fact, we can, in fact, show that if a program evaluates to something in C step, then it evaluates to the same thing in the earlier small step semantics. Using the equivalence theorem that I think we will skip. I will just run through it. It's sort of following the same description as how we describe the relation between big step, small step, and small step, big step. Anyway, so yeah, that's really what we have here. I skip it because it's not important. Yeah. All this says is that let's just I can just mention this. So if you have a VC and you take the original small step relation and it goes to V prime C prime, then if you take VC, you can also use the same the new C step function to go to V prime C prime, and you can also go the other way. You just have to use intermediate lemmas. This is all of this is in the operational semantics lecture, the original file, right? But I'm sort of skipping here. You can also go in the other direction is what this is. This is unsurprising, right? We've not done anything interesting, but if you want to convince Hawk, then you have to write these theorems down. So what's the payoff, right? That's where we really want to get to. As I mentioned, if you add interesting structures to your program, then this evaluation context sort of makes it easy to separate out interesting things from boring things, right? Essentially, in this example, what we are going to do is to add a construct for parallel execution in the command language, right? The sequential command language stays the same. The only construct that we add is this parallel composition operator. It's a really funny one. So all you're saying is that I can execute things in parallel, right? And left and right are C. And the idea is that this C and this C can execute in parallel, right? And the way, I mean, this is all very abstract, right? Because we actually have to give semantics for what parallelism is. Coq doesn't understand parallelism. We are actually going to give the semantics for what parallelism is. What's the intuitive meaning of parallelism, right? because we described everything as small step semantics, when you have a command such as this parallel composition, you can either reduce the left-hand side or reduce the right-hand side and take a step, right? If you take a step here, then this one remains the same, and the whole thing reduces to whatever the result of this one is, followed by the same thing here. Or you can do the other thing, right? So this is the non-determinism that you have, right? This particular construct introduces non-determinism, where you can either take a step on the left-hand side or the right-hand side. I mentioned non-determinism. The thing that I didn't mention earlier is that the semantics so far for our language is deterministic. You give a command, if it reduces to value, you give a same command again, it reduces the same value again for all executions. But that is no longer true when you have concurrent executions, because let's say this assigns 1 to x, this assigns 2 to x. Based on which runs last, the value of x could be different. How do we actually capture parallelism, right? This is all fine. Intuitively, that is what the meaning is. So the way we capture it is very, very, very simple, right? All we are doing in this evaluation context now is we are adding 2 new contexts. And this is very clever, right? All we are saying is that if you see this parallel construct, you can either focus on the left-hand side or focus on the right-hand side. And that's it, right? So this actually gives you these extensions, this syntactic extension, this extension, along with what we've defined earlier, actually gives you a parallel language. We don't have to change the step 0 function, right? If we did not have evaluation context, we have to sort of, you can try it, it just sort of pollutes everything. This particular thing will have to sort of appear everywhere. But now what we've done is we've sort of split the parallel notion of a language from the sequential notion. So all of the reductions here in step 0 happen to be sequential, right? They don't involve parallelism at all. But all the parallelism is captured here in these in this evaluation context. And the only thing that we add, just for the sake of completeness, is that we add this notion of a garbage collection of completed threads. So what's the idea here? We say that if we ever get to a command, right, where the command is skipped, so the left-hand side has completed evaluation, and you have some other C, then you can take a step where you throw away that left-hand side thread, right, the context of the thread. This is there so that you can reason about, you can say something about the final state. If you have these skips lying around, then the final states will have skip, composition, skips, composition, skip, so on, right? Really, what I want to say is that I take a program that might have parallel things. I can always say, with the help of this GC rule, I can always say, if the final command happens to be skip, then I will say something about the final state. And that's the only reason we add this garbage collection thing here. But otherwise, everything just works out. Actually, that's all we have. So let's look at how this works in practice. Right. So here is a concurrent module, right? And I have the commands the same as what I had earlier, except I have this new command now, right? I have this parallel command, which takes 2 subcommands, and the idea is to run them in parallel. I again introduce notations. I add these parallel bars, and the way to read that is parallel composition. So it runs the left and right commands in parallel. Now we extend the context, right? We had a whole and a sequence. Now we add one context for reducing the left-hand side, and one for reducing the right-hand side, right? And now we also have to equivalently extend the plug with how to plug when the context is C power 1 and C power 2, right? The definition itself is straightforward, right? So if you happen to have a C power 1 as the context, right, where the context happens to be C here, right? C is the context, and the command that you fill in is C. If you can plug in the uppercase C with lowercase c, and you get a C prime, then this whole thing just becomes a command which is parallel C prime C2. And similarly for the other case, right, C par 2, where if you fill in this capital C with this small c, you get a C prime, then this whole command becomes parallel C1 C prime. So we will use it both forwards and backwards, right? We will sort of at every step we will sort of go backwards, try to take a command that appears like this to destruct it into an evaluation context, either this one or that one, and then the command. We will apply step 0 that reduces to a command. We will plug it back in and then say that, oh, now you can plug it back in and get back to the command. So that's what we are going to use this relation for. Observe that, a nice point is that if we had defined this as a function, then we wouldn't be able to do this backwards reasoning, right? From the result, how do you split it? But because we've defined this as an inductive, we can go backwards and forwards. I mean, this is the whole point of logic programming lecture, right? That you can do both forwards and backwards reasoning. We are using the same idea here. Step 0 actually remains the same, except for this one extra command, right? Which is this garbage collecting completed threads. So when you have a parallel skip C, it just goes to VC. But otherwise, all of these are just the same as what we've seen earlier, right? C step is exactly the same thing. So now no change in C step because we've sort of put in all of the smarts into this evaluation context. So in order to illustrate program execution, right, that this is actually real. So here is the classic example, right, which says that if you happen to have a parallel execution where you don't lock the critical section, right? Actually, you don't put a lock around some shared state, then things can go wrong. So here are two threads, right? So the first thread is reading an n and then reading into a local variable a, right? And then doing a plus 1. So it's incrementing n. Similarly, this is reading into b, local variable b, and doing b plus 1, right? So we expect, the programmer expected that if you start with n equals 0, then you end up with n equals 2. But of course, you can read 0 here, right? And then write 1, and this also can write 1. So the observation here is that there are multiple executions here, right? So one of the executions actually gives the right value. So if you completely execute, say, the first thread, and then do the second thread, you'll see the right answer, or the other way around as well. But there are executions which go wrong, right? So that is what we want to show, just as an illustration of saying that we are in fact capturing concurrency, right? And then yeah, this is for automation. I add this plug step 0 and C step as constructors, so that's done. So first, we want to show that first we want to show that the correct answer is obtainable, right? Which is to say that if I execute, so the way I'm going to proceed is that I believe if I execute the entire first thread and followed by the second thread, I'm going to get the right answer. How do I define the right answer? If you start with n equals 0, right? And then you apply multiple steps of C step star, and this eventually goes down to V skip. The program has completed execution. Then actually not n equals 0, n equals some n. Then n is n plus 2, right? For all n is n plus 2. So this is intuitively what we expect in some correct execution, right? And observe that this garbage collection rule is actually helping us here, because there were two threads. We can just write this as skip because the garbage collection throws away one of the threads. So we can show that this happens. All we have to do is pick the right term to focus on to evaluate at every step. Okay, so we do EX as propositional just to get rid of the existential variables and do propositional reasoning. Let's unfold the program, right? And transitive flexible closure. So you do that to do one step of the C step, and then multiple steps of multiple succeeding steps. So here is an interesting application, right? So how do we actually inform Coq that we want to pick, there is non-determinism here, right? But we want to say, I want to reduce this term by choosing a particular subterm, right? In particular, I want to say that I'm going to reduce this term, this command here, by focusing on the left-hand side. The way you do that is you sort of just give um, the term that you want to unify for the evaluation context. Okay, so we are going to do C step. Essentially, C step is this function here, right? So this inductive relation here, and I'm going to tell Coq what is the assignment for this particular C. Right, there are several ways to, I mean, there are at least two ways to execute this. You can either take a left one or right one. I'm actually going to fully describe what that evaluation context is. Um, and the way I describe it is you make the evaluation context to be C power 1. So that is going to focus on this term here. Oops, sorry. The term on the left, right? And then I say, then do sequence whole, which means then focus on this term, and the whole appears here, which means that the subcommand that I'm actually going to reduce is this term, right? I'm going to focus on the left-hand side, and I'm going to take a step on the first command in the sequence, right? And because this works by unification, I don't have to give the assignments for the other one. Coq just finds the assignments there. So I'm doing E apply here. That's why it works out. So all I'm doing here is that I'm sort of informing Coq when you apply C step, right? C step, when you apply C step, this is an existential variable, right? So this uppercase C does not appear in this term. Only lowercase c's appear. And I'm just giving a particular pattern for this uppercase C so that I can inform Coq which one to reduce. That's the only interesting bit in this whole theorem, right? Otherwise, everything is going to look very simple. We're going to apply that over and over again. So let's just look at what will happen, right? So when we do this, so we get this plug, right, where we actually end up getting a term here which matches the term that we've given here, right? These underscores have been filled by unification variables, right? And then I say that I am going to reduce the actual term. So this is going to, so this will be unified with, eventually this will be this unification variable question mark C will be unified with this one. Right? Let's step through that. Now, because I've given the exact pattern, I don't have to do much. So I have to apply E constructor that says, so I'm going to split this into left and right. And this is going to be sequence of the whole. So this is going to be the command that I'm going to actually get for C0. So if I do one more thing, it says, oh, now the context is plugged this whole with this command, and the command that I have is just the assignment command. So so there is only one rule that one fact that satisfies this one, which is that if you plug a command with if you plug a hole with a command, you get the same command. So this question mark C has to be this command, right? So that is satisfied. Now you get the right step 0 function, right? So it actually focuses on the assignment. This is again direct application of the assign step 0 assign step. So that goes through, and you get an assignment here, right? Um, so Okay. Yeah. Sorry. So that's what. Thanks, Session. So I just yeah, it's a pain. So my phone is connected to my headphones as well. So I got a call which was answered automatically because I pressed the wrong button. So it got connected to the call and audio got routed there. I cut the call, but I didn't get the audio back to this one. So can you hear me now? Okay, cool. So what we have here is essentially we've done the step, right? So we just have to plug this back in to get the right assignment variables. So there's nothing interesting going on here. These are like direct applications of the plug rules, right? So if you plug a hole with this command and then you plug that with skip, what do you have to get? So you sort of keep doing that. And if you plug a hole with skip, you just get a skip. And eventually what we've done, we sort of split this into smaller steps by splitting it into evaluation contexts. We've done a step 0 reduction, right? Interesting reduction, and we've sort of plugged it all the way back in. So all we've done is we've reduced this assignment, right? Which is read n and then assign a to that value. Um, yeah, if you simplify, you'll sort of see what is happening. Yeah. So we've read n and then stored that value into a. Right? All that's happened is that one. This is very, very mechanical, right? If you sort of see, all we had to do at that step is we needed to say what is the structure of the evaluation context. And by structure, we are sort of saying which part of the command that you are reducing. This is really what we want to say, right? We want to show that if you focus on executing first thread and then second thread. So that's the only manual intervention that we want. All of these are repeated applications of e-constructor. And because we've hinted these constructors, e-auto will make it go through, right? So again, e-constructor once for splitting it into, I mean, we had a transfer flexible closure, so we apply TRC front constructor here. So C step and something else. And then we provide which one to execute. So we are going to say, I'm going to evaluate the left-hand side thread C par 1, and I'm going to put a hole here. So which means that this entire command is the one that I'm going to reduce with step 0, which is what we want. And I'm going to do repeated applications of eauto so that I get to a state such as this one. That reduced as well. So all that has happened is the skip is gone now, right? And now I want to say reduce cpar1 with this entire command, cpar1 with the hole here. I don't care about the other one. So that goes through, and again, I'll simplify so that you can see what is happening. So n becomes n plus 1, right? I have a skip here. I want to say apply the GC step, right? I just want to get rid of this one. So e-constructor. Actually, yeah. So this entire thing is the command that I want to reduce. So I just say that the evaluation context is a whole, which means that this entire thing becomes the subcommand that I'm evaluating. So skip is gone, right? All that is done is skip is gone. I simplify again. That's fine. Now we have, we don't have a parallel construct. That's gone, right? Now all we have is sequencing. So I'm saying that the next thing I'm saying is that do sequencing and the whole has to be the first term. So this command will fill the hole and eauto, right? Let me simplify so that you can see that B is also n plus 1. B is n plus 1, right? And the command is skip. So one more step to remove skip. And I'm going to reduce the assignment as the final one. So if you do that and say simplify, you will see that now n is n plus 1 plus 1, right? This is what we wanted. And now this is skip, right? And we are going to apply TRC ruffle. So transfer flexive closure is actually reflexive. So just E constructor makes it go through, right? And you simplify, you get the proof, right? So we assigned it, that went through, F equal ring makes it go through. That's the right answer. So we also want to say that we can get the wrong answer. The wrong answer, I think what we are going to do is to evaluate the first step here, evaluate the first step here, and then evaluate the second step here, evaluate the second step here, we'll get the wrong answer, right? So same thing as before, same program, right? Except that I'm saying that when this program terminates, the answer that you will get is some n+1, right? Not n+2. We will miss a increment. So again, the same thing. So firstly, we are saying that do C par 1, right? E auto, that reduces to a skip. Next, what we are saying interestingly is reduce the second thread, right? And the first command in the sequencing in the second thread. So we are reducing this one. This one will go to a skip now, right? So that goes to a skip. Actually, you can't see. So let me simplify. Yeah. So skip and skip, right? That's it. So all the damage is done. So now if we just go through with it, right? Execute one step of the first thread, right? And then one step of the second thread, one step of the first thread again. Now, yeah, just continue with the evaluation and finish up the evaluation. The damage is done at this point when we choose second thread to evaluate. Simplify, let's simplify. Right, so this is n+1. That's the wrong answer. And if you apply E constructor and simplify, you will see that n+1 is n+1. We are showing that we can get the wrong answer. Right, so that's it. Even though this is a very simple program, what we've done is really nice. Right? So what we've seen is that we can encode the semantics of a concurrent programming language, right, very easily by taking the small step semantics for the sequential part, and then using evaluation context and just introducing non-determinism, right? Two ways of evaluating the same command, and the clever bit is just this, right? There is only one clever trick here, which is that given a command, you can either apply. These two are the same commands, right? This parallel, this one, and this one can be the same command. You can either choose to reduce the first thread or the second thread, and that's it, right? Once you do that, you actually get all the nastiness of non-determinism. Let's put it that way. Yeah, so that is all I wanted to say about operation semantics. We will actually use operation semantics a lot in the rest of the lectures. Operation semantics underlies how we tend to do a lot of proofs in the real world. So I'll describe a small language, give operation semantics, prove some properties on it, right? So this is very, very fundamental. This sort of operation semantics is sort of keeps coming back all the time. I think I already shared links to the operation semantics for the ARM processor and the WebAssembly interpreter. This is, if you pick up one idea from this course, then describing the semantics of interesting programs using operational semantics is what I wanted to pick up. So I will release the assignment where you have to deal with non-determinism, right? It will be a fun assignment, but you'll have lots of time for the assignment. You don't need to start the assignment now. You can save it and start it later. Okay, I'll stop here. So in the next lecture, what you're going to see is Lambda Calculus, right? So we are going to again refresh our ideas that we saw in 3100, but we are going to take a different route. What we are going to focus on is verifying some nice properties, right? We had this strongly normalizing property for simply type Lambda Calculus. We will actually show that simply type Lambda Calculus is strongly normalizing. Prove it, right? We just won't take it as a fiat, right? I just tell you, and you sort of take my word for it. You will actually show, you will actually prove it that simply typed Lambda calculus is strongly normalized. We'll get to that eventually. There is a lot of ideas in the course of it you will pick up, but that's what we are going to see in the next class. Okay, I'll stop here. I'll see you tomorrow. Thank you. Bye bye.